Okay, so I'm assuming that is fine. So as I said, what we'll do is today we'll start the discussion with an understanding of vertical circular motion and the standard techniques that we use, including conservation of energy in that. And then towards the second half of the lecture, we'll discuss some of the questions from H.C. Verma exercise for circular motion. So let's start with the basics of vertical circular motion. So the most standard example of vertical circular motion is when we have this kind of situation. A particle tied to a string or a massless thread, okay, and that is suspended from some point on a ceiling, like this example here, something that looks like a pendulum, basically. So the motion of a pendulum is part of a vertical circular motion. So we have a thread of length L and a particle of mass M attached to it, vertically like this. So this is a light thread, okay, and this is a particle. So when it is in the equilibrium position over here, yes, Bhargav, that is correct, that the maximum speed that is safe to drive on the curved highway or a section of the highway which is curved. So the maximum speed that is safe such that there will be no slipping is determined by the banking angle concept along with the coefficient of friction. And of course, in real life engineering systems, the maximum velocity or any such limiting value is always given such that there is quite a bit of margin. So if the specified maximum velocity is a certain value, then the slipping will actually start occurring at a velocity even larger than that maximum value. So there is some margin for error within that also, because different type of tires will have different coefficients of friction. Okay, and also depending on the temperature of the surface of the road and weather conditions and all. So there are all these other factors which also determine the limiting values. So the maximum specified velocity for negotiating a turn on a highway is taken into consideration with all these factors. Okay. So hope that makes it clear about that. But banking angle is a part of the consideration in that, of course. Okay. Okay, now coming back to this, so if we have this kind of a situation, a particle attached to a light thread, and what we do is at the bottom, when the particle is at this position initially, we give it an impulse or a sharp push so that it develops a horizontal velocity just at that moment equal to V0. So what will happen is that because it is attached to this thread, the particle will describe vertical circular motion about this suspension point O. So from this point, so if the particle is given a sharp impulse or a push, okay, horizontally at the lowest position, okay. So from that point, what happens is it starts a vertical circular motion. It starts a vertical circular motion about or with respect to the point O as the center, about O, which is the point of suspension. Okay. So such an example is a case of what we call vertical circular motion, because it is circular motion in a vertical plane. So the definition of vertical circular motion is it is circular motion in a vertical plane. Most of the examples we've taken earlier are not this. They're examples where the circular motion was happening in a horizontal plane. The plane of the circular path, it was a horizontal plane. Here the plane of the circular path is a vertical plane. Like the last example we did in the previous lecture. That one was an example of vertical circular motion. So what will happen here now is that if we compare the position of the particle from where it started at the lowest point with the position after some time. So that's the next thing we'll do now. We'll compare that in a certain amount of time, the particle has gone from here to now somewhere over here. So it's made an angular displacement of some theta about the center of its circular path, which is this point of suspension. So this is the angular displacement the particle has made, theta, in going from this point via a circular path like this to this point. So accordingly, its velocity vector would have changed both in terms of magnitude as well as in terms of direction. Now let's understand why it's changing in terms of direction, because tension is providing the necessary centripetal acceleration or the centripetal force to keep turning it such that the velocity always remains perpendicular to the spring, and that's what keeps it in circular path. And on the other hand, the gravitational force acting on it, there is a component of it which is acting opposite the velocity, so that is providing the tangential deceleration. Okay, so this is the vertical circular path. So as you can see, v will become less than v naught. Okay, so this is the point A and this is the point B. Now if you look at the forces acting on the particle next, so if you look at the forces at the point A, there was mg acting like this, and there is tension in the string acting like this. By the time you come to the point B, mg is acting like this and tension is acting like this. So T is like this, mg is like this, and you can see that this angle here is theta, whereas here, let's say the tension was T naught, the weight was mg. So if you look at the free body diagram at the point E, what is happening is T naught minus mg should be equal to mv naught square by L. Okay, that means T naught minus mg is the centripetal force. It's the force pointing towards the center. Okay, and tangential force is equal to 0. So therefore, at this point A, okay, the centripetal acceleration is v naught square by L, but the tangential acceleration is 0 because tangential force is 0. But contrast this to the position B. Now at the position B, you can see what is happening. Okay. mg is acting like this and T is acting like this, where this is the tangential direction and this is the radial direction. Okay. So this angle was theta. So you can see that if you take components of mg, then if you take the components of the weight, so there is a component of weight along this direction, which is mg cos theta, and there's a component of weight in this direction, which is mg sin theta, whereas this force is tension. Yes, because that's correct, Bhargav. Okay, so what's happening is in the next diagram we can see that by the time you reach any other position after B, there is this mg sin theta component that is acting in the direction opposite to the velocity now. So it's creating tangential deceleration because this is the direction of the tangent and this is the direction of the radial line. So at the point B, what you can see is that T minus mg cos theta, that should be equal to mv square by L. This is your centripetal force. It's pointing towards the center. Whereas your tangential force, that is mg sine theta. So that is providing a tangential acceleration. Now see the direction of the tangential acceleration. The direction of the tangential acceleration is backwards. It's opposite to velocity. So at the point B, what we can see is that the tangential acceleration, which is g sine theta, is minus of dv by dt. So it's actually a tangential deceleration. From here, from this equation, you can see. So there is a tangential deceleration, which is provided by gravity. And that is why the particle speed is slowing down as it is going up. Because of this continuous tangential deceleration provided by mg, provided by the sine component of weight, the particle slows down. Okay. So the speed v is decreasing as theta increases from 0 to whatever 180 by the time it reaches the top. Okay. So the speed is decreasing because of mg sine theta. It provides a tangential deceleration. That is the important thing. Yeah, so people, let's understand this in more detail. So if you look at the free body diagram at the point B, it's clear to you what is happening, that the component of mg that is acting along the tangent this mg sine theta component here, this one, it is acting opposite to the velocity. So it's creating a tangential acceleration in the direction opposite to velocity. This is opposite to v. So that is why it is minus dv by dt. So that is the one that is creating deceleration. Yeah, I'll take you back to it. Okay. Whereas the centripetal force is how much? The centripetal force is this value, T minus mg cos theta, pointing towards the center. That one is the centripetal force. So in any circular motion, when we write net force is equal to mass into acceleration, we divide the acceleration into centripetal plus tangential. So the net force also we divide it into like this. The centripetal force is mass into centripetal acceleration. The tangential force is mass into tangential acceleration. So here that is what we've done. Each of these equations is doing this. This is the centripetal direction and this is the tangential direction. And likewise earlier here we saw this was the centripetal force, this was the tangential force. Tangential force was 0 at A. So that's why the tangential acceleration was 0. Finish writing down this part now, Bhargav? Okay. Okay, done now. Okay, so now see the other important aspect here. One is the free body diagram, and we just saw from the FBD at the point B, we are having those two equations. Now the other important thing is that from the point A to the point B, okay, at any point in between, okay, including A and B, of course, okay, tension acts perpendicular to the velocity, the instantaneous velocity v, because tension acts along the thread. So it is centripetal, it's pointing towards the center. And the velocity is tangential. Okay. So therefore, work done by tension, which should be integration T dot ds, will become 0, because displacement at any instant is velocity into time, and tension is perpendicular to velocity, so their dot product is 0. Okay, so just like in a normal situation in work energy, you see that work done by normal reaction is 0, because it is perpendicular to the instantaneous displacement. So like that, the work done by tension is 0, because it is perpendicular to the velocity. So dot product of tension and velocity is 0. Okay, the angle between them is 90 degrees, so cos 90 is 0. So work done by tension is 0. So work done by tension is 0. So therefore we can say, therefore for the particle plus the earth as a system, okay, mechanical energy is conserved. That is the sum of kinetic energy plus gravitational potential energy is constant. Okay. This is gravitational potential energy, and this is kinetic energy. Or another way of expressing the same thing is that the change in kinetic energy plus the change in gravitational potential energy will be 0 from A to B. Okay, so these become the two important aspects that we use for solving any vertical circular motion. One is the free body diagram. Okay, yeah, see, I'll just explain this concept once more, then we'll come back to this. You have studied the general expression for work done. Work done by a force, कैसे define करते हैं उसको? We define it as integration f dot ds. ऐसा होता है ना, if a force is acting on a particle and the particle is moving on along this kind of path, so at any point of time you take the differential displacement, so the work done during that small displacement is f dot ds. So the total work done becomes integration of this, it is integration f dot ds from initial to final position. You have seen this in work energy, right Norman? Okay, तो अभी देखो यहाँ पे क्या हो रहा है, when we look at the force of tension in particular, okay, when we look at, I want to calculate work done by tension, so it is integration t dot ds. This is the work done by tension. Now what is happening at any point of time, the direction of tension will be perpendicular to the direction in which that differential displacement is happening. So I'll just make that diagram here so that it's clear. So for example, if I see here, then after some time the particle is here, and after some time the particle is here. So it's going in the circular path from point to point. Like this, okay. So when it's here, for example, the tension is acting in this direction along the string. When it's here, the tension's direction is changed like this. The tension's direction is continuously changing from point to point. Okay. So this was the tension at this point of time. This is the tension here. This is the tension here, let's say. Okay. Whereas the velocity vector and therefore the differential displacement vector, वो कैसा होगा? यहाँ पे ऐसा होगा. It's along the tangent. So it will be like this. Okay. यहाँ पे ऐसा होगा. Now from here it will be like this. Okay. So always the differential displacement is the instantaneous velocity into time, into small time dt. So this is along the tangent. So the differential displacement is also along the tangent. So therefore it is perpendicular to the tension, because the tension acts along the centripetal direction and displacement therefore is acting along the tangential direction. Okay. So that is why tension is perpendicular to the displacement at all points of time. So in fact we can also write another part of this, that T's dot product with ds will be 0, because this is tangential and this is centripetal. So they are perpendicular to each other always. Okay, so Norman beta, this point is clear now? Okay, very good. Okay, so tension is just acting in such a way that it's all at every point it is perpendicular to the instantaneous displacement ds. So for every small displacement ds, the work done by tension is 0. So that means the total work done by tension going from this point A, let's say, to this point B, the total work done will also be 0, because at every point in between t dot ds is 0. So integration t dot ds will be 0. So now in this system, mg is our internal conservative force and tension is not doing any work. That means there is no work done by external force. Okay. Your general equation of work energy theorem is that work done by external plus work done by non-conservative is change in kinetic energy plus change in potential energy. So in this case, external force is not doing any work. Tension is not doing any work. There is no non-conservative force like friction. So That's why the change in kinetic energy plus change in potential energy is zero. Okay, and that's how we get that mechanical energy is conserved. That is the sum of kinetic energy and potential energy is remaining constant. This statement is called the conservation of mechanical energy, as you know. Okay, people. So hope this is also clear. Yes, dt is a very small change in time. Okay, so that is a kinematics relation, that instantaneous displacement ds for a very small time dt is instantaneous velocity into time dt. This is a kinematics relation. We define instantaneous velocity as rate of change of displacement. So in a very small time dt, the displacement becomes vdt. So for example, if we have a instantaneous velocity of 3 I cap plus 4 j cap in meters per second. Now I ask you, what is the displacement in time dt equal to, like, let's say 0.01 milliseconds. That's a very small interval of time. So the displacement will become v dt. So that will become 3 I cap plus 4 j cap multiplied by 0.01 into 10 raised per minus 6. Sorry, 10 raised per minus 3. So this is in seconds, this is in meters per second. So this will become 0.03 I cap plus 0.04 j cap, whole thing into 10 raised power minus 3 meters. Or we can say 0.03 I cap plus 0.04 j cap millimeters. That will be the displacement in that small time. Okay. Or for example, if we know a variable velocity, which is given by something like this, 2t I cap plus t square j cap. Okay. Now I ask in this that this is not related to circular motion. I'm just giving you an example of how this thing works in kinematics, general kinematics. So suppose we have a variable velocity given by this. Now I want to find out instantaneous values, velocities value, and mod of instantaneous velocities value at the instant t equal to 1 second. Okay. Then I ask you the small displacement from t equal to 1 second to t equal to 1 second plus dt, where the time dt is this value. Okay. And then I ask you what is the total displacement from t equal to 1 second to t equal to 2 seconds. Okay. So I'm moving away from circular motion for a minute over here, but it's worth it. We're just doing a bit of revision of kinematics. So this is how we apply calculus in kinematics, calculus as well as vectors concept. Let's see how we'll calculate each of these. Just try this out. So just use this concept over here. Okay. Use the concept that instantaneous velocity is instantaneous rate of change of displacement with respect to time. So a very small displacement can be directly written as velocity into that very small time. But a total displacement s will become integration of velocity with respect to time from whatever time t1 to whatever time t. So this is the displacement in the interval t1 to t2, whereas the one above that we have written ds, this is in very small interval of time dt. So understood the difference between the two things now. Now this example will make it even more clear. So just try this out. Then we'll come back to our circular motion example. But since you have asked this question, I would like to make this 100% clear. How we relate the instantaneous displacement ds in a very small time dt with the instantaneous velocity v. Yeah, anybody got the answer for this? Bhargav, have you tried this out? The second question below, just tell me the answers. Yeah, at t equal to 1 second, that's correct. The magnitude of velocity will become uh, root 5. Velocity's value at t equal to 1 second will just be this now, 2 into 1 I cap plus 1 square j cap. So that is 2 I cap plus j cap in meters per second. Because I'm assuming this is given in meters per second. So that's the first thing. This is the velocity's value. So the magnitude of the velocity at t equal to 1 will become mod of 2 I cap plus j cap. So that is root 5 liters per second. Okay, so that's the first part. So now for the small interval of time dt from t equal to 1 second to t equal to 1 second plus dt. For this interval, the differential displacement will be instantaneous velocity multiplied by differential time. So the instantaneous velocity we just saw, it is at that moment it is 2 I cap plus j cap. And that small interval of time, this dt is given to us to be 0.01 millisecond. That's given in the question. So that is 0.01 into 10 raised power minus 3 seconds. So this will become 2 I cap plus j cap into 10 raised power minus 5 meters. Or we can say that differential displacement will be 0.02 I cap plus 0.01 j cap in millimeters. This will be the displacement during that small time. So hope this is also clear. Yes, because the time interval is very small, na? So we are taking the velocity for that time interval to be the instantaneous velocity at t equal to 1 second only. Because between 1 second and 1 second plus 0.01 milliseconds, that the velocity is hardly changing. Na? It's like between 1 second and 1.000001. Because 0.01 milliseconds is 10 raised per minus 5 seconds. So this interval of time is basically between t equal to 1 second to t equal to this much seconds. So it's a very small interval of time. Or 0.01 milliseconds. So for this small interval of time, there's hardly any change in velocity. No? So it's instantaneous velocity into differential time dt. That becomes the very small displacement. And likewise, you can see the displacement is very small. It is actually of the order of micrometers, no? Because 10 raised per minus 6 is millimeters, micrometers. So it is like 20 I cap plus 10 j cap micrometers. Another way we can write this is that it is 20 I cap plus 10 j cap in micrometers. And units dimensions, you must have studied about micrometers. 1 micrometer is 10 raised per minus 6 meters, or 1 millionth of a meter. Okay, and now if we move on to the third part of the question, anybody's got that? So for the third part, what is happening now? It's a large interval of time, 1 second to 2 seconds. So we have to use integration. So for the third part, we'll use this, that the displacement is equal to integration of velocity with respect to time, because it's a variable velocity. Had it been constant velocity, we could have said velocity into time, but because it's variable, we have to use integration from t equal to 1 second to t equal to 2 seconds. So now we just substitute this thing. So it is 2t I cap plus t square j cap integrated from 1 to 2 seconds. So 2t's integration is t square, and t square's integration is t cube by 3. And in this we have to put the limits from t equal to 1 second to t equal to 2 seconds. So you can see this will become 2 square minus 1 square I cap plus 2 cube minus 1 cube by 3 j cap. Okay, I'll just check the answer. Okay. So you can see that the displacement is coming out to be 4 minus 1, that's 3 I cap, plus this will be 7 by 3 j cap in meters. So this will be the displacement from t equal to 1 second to t equal to 2 seconds. Okay, no problem. But method is the more important thing here. So actually, this is not important for the circular motion thing we are doing right now. Since you asked how we got that relation ds is equal to v dt, the logic of that. No? So I'm just, this is just like a quick revision of the concepts of calculus applied to kinematics. You know, the concept of instantaneous velocity and the concept of displacement as the instantaneous velocity integrated over time. Okay, so anyhow, people hope this is clear. All right, so let's now come back to vertical circular motion, what we are discussing. Okay, so let's quickly see what we had understood so far, that if a particle is going in, particle attached to a thread is going from this point to, let's say, this point. Okay, in a circular path like this. Okay, and its velocity vector here was v naught, and its velocity vector here is v. So let's quickly write the relations that we could develop using the concepts we have just discussed. So weight tension weight tension. So this is a point we had taken as A and this is a point as B, and this angular displacement was theta. So first of all, we had seen that at the point A, we have T naught minus mg is equal to mv naught square by L. Okay, and we had tangential acceleration equal to 0 because tangential force itself was 0. Whereas at the point B, we had T minus mg cos theta, because if we just extend this line, you can see this angle is theta also. So that is the centripetal force. So it is equal to mv square by L. Okay, so that's the centripetal one, and mg sine theta is equal to tangential acceleration, and this tangential acceleration is actually minus dv by dt. Okay, and then the other thing we saw is we can also apply work energy. Okay, so secondly, conservation of mechanical energy. Okay, because work done by tension is 0. Okay, so we apply that conservation of mechanical energy, then we can see that suppose this height difference between the 2 points A and B, if this height difference is h, then going from A to B, so this is the next equation which is important for us. Going from A to B, change in kinetic energy plus change in gravitational potential energy is 0. So half mv square minus half mv naught square, that's the change in kinetic energy, plus mgh, that is the change in potential energy. This should be 0. So that becomes another important equation for us. So this is the set of equations that we use to solve any type of situation where we have vertical circular motion of a particle like this attached by a thread. It can be attached by a thread, it can be attached by a chain or rod or anything like that, as long as that one is massless. Now only the particle has mass. Yeah, Bhargav, this is the same thing in the last part of the circular motion thing. So just note this down first, then we'll do a numerical example. I'll take you back when we are discussing the numerical example. Sorry, this is not the example, this is the concept of the vertical circular motion. Okay, L is the length of the chain. So this is again the centripetal direction that we're taking. And this is the tangential. This is again the centripetal component of the F is equal to ma equation. This is again the tangential. Okay. Okay, so now let's see a numerical problem related to these equations being applied. So we have a given situation like this now. So in this example, the length of the thread is 20 centimeters long. We'll take acceleration due to gravity as 10 meters per second square. Okay. Now, at the lowest point, okay, the particle of mass m is equal to, let's say, 500 grams is given horizontal velocity v naught of let's say 2 meters per second. Okay, so first thing, find the tension T naught just after it is given the horizontal push at the lowest point. Okay. Then secondly, at angular displacement, theta equal to 53 degrees from the lowest point. Okay. Calculate speed of the particle v and find the tension, the centripetal acceleration and the tangential acceleration at theta equal to 53 degrees of part 2. So what we discussed in the above part, we will just learn to apply it numerically now in this question. Through this, we will learn the whole way of solving vertical circular motion problems. So the fundamental equations that we use are the ones we saw above, the FBD equation and the conservation of mechanical energy equation. So we have to just implement those equations with these numerical values now. So just try this out, people. Okay, so first thing, let's check out the free body diagram at the point A. So first part at A, you can see that tension and mg, whereas the speed is v naught, part of this circular path. Okay, so we have okay, so 500 grams was the mass. So zero point 0.5 into 10 plus 0.5 into 2 square divided by zero point 0.2, because the length 0.2 meters, that is 5 plus 10, 15 newtons. Very good. So the tension T naught at the initial point is 15 newtons. Okay, so very good, Jay. You got this correct. Okay. Now next, what we have to do, we have to find, next thing in the second part, we have to find the speed at the point V. So for this, what you do, you use conservation of energy. Conservation of mechanical energy from A to B. You use that. Yes, anybody got the answer for the speed? So let's see how we'll work that out. Okay, so I want to find the speed. So now I'll just concentrate on the vertical displacement part first. So if I drop this perpendicular, you can see that this distance from here to here, it is what? It is L cos theta. Because in this right angle triangle, you can see this side is L, this side is Y, and this angle is theta. So Y by L is cos theta. So that is L cos theta. Okay. So now this height, this is what I need to calculate. So H will become L minus Y, or L minus L cos theta. Okay, so in this particular case, H will become 0.2 into 1 minus 3 by 5, because theta was 53 degrees. This is the height through which the particle is climbing from A to B. Okay. This total length is L. Yeah. So this triangle here, that's this one. So this is clear, I hope, to everybody. So now you apply work energy. So from A to B, change in kinetic energy plus change in gravitational potential energy should be 0. So V square will become V naught square minus 2GH. So now V naught, remember, was given to us as 2 meters per second, and V we had to find out. So this will be our V. Okay, so as you can see, the speed has slowed down from the initial value of 2 meters per second to nearly 1.55 meters per second because of the loss, because of the gain in gravitational potential energy. There's a loss in kinetic energy.
कॉल केला गेलेला नंबर त्यावेळेस नेटवर्क कव्हरेजचे संपर्क क्षेत्रात
Okay, so that's the second part done. Now we want to find the tension and the centripetal acceleration and the tangential acceleration at the point of 53 degrees. We want to find at B, we want to find the tension, the centripetal acceleration and the tangential acceleration. So what we'll do is in this free body diagram at the point B, we will just resolve the mg into the two components. So tension mg cos theta, mg sin theta. Okay. So this is our tangential axis, this is our radial axis. Okay. And we have just found out the value of V. Yeah, so I'll just verify the value. So T minus mg cos theta should be equal to mv square by L. Right? So this is our centripetal equation. This is our centripetal force equation. And mg sin theta, this is our tangential force equation. Okay, so from equation 1 we can see that tension is mg cos theta plus mv square by L. So 0.5 into 10 into 3 by 5, okay, plus 0.5 into, now remember V square was, or basically V had come out to be square root of 2.4. Yeah, V was square root of 2.4 meters per second at the point B. So make use of that value. And L was 0.2 meters. So this tension is becoming 3 plus, this is 2.4 into 5 by 2. So 1.2 into 5. So 6. Yes, very good. That's correct. The tension is becoming 9 newtons. And centripetal acceleration, that's V square by L. So that is 2.4 divided by 0.2. So that's as much as 12 meters per second square. whereas tangential acceleration is g sine theta. This is from equation 2 above. Okay. So that is 4 meters per second. So, oh, sorry, 8 meters per second. We take g as 10. But just keep in mind that this is a tangential deceleration. It's minus dv by dt. This is a tangential deceleration. How deceleration? Because again, see the direction of v. No? It is opposite to the tangential acceleration. No? See, the tangential acceleration is in this direction along g sine theta, and the v is opposite to that. No? So it's a deceleration. Understood, na, Harsh? Okay. Okay. Very good. Now let's do another question to understand another special case of this vertical circular motion. So if this is what is happening in a circular motion, okay, that it's suspended from the point O. So the particle goes like this, reaches the 90-degree position and just comes to rest. So it just momentarily stops at the 90-degree position. So at this position, its V becomes 0. So obviously it has been given some V naught at this point. Okay. So given that the length of the thread this time is 80 centimeters, find V naught at lowest point if the particle just reaches the theta equal to 90-degree position. Okay. So just reaches theta equal to 90-degree position means it stops momentarily at theta equal to 90 and then returns back. So it goes in an oscillatory motion. So the path of the particle will be like this. Go from here to here, then it will stop here, then it will come back by this path, then go from here to here, stop on the other side, then come back. So it will keep oscillating between these points. And every time it will go back to the same height, and every time it comes down, it will have the same speed because mechanical energy is conserved. So this is the same situation. It's a light thread attached to a particle which is doing vertical circular motion, but such that from the lowest point is given the speed v0 such that it just about reaches the 90-degree displacement point. The angular displacement, the maximum value is 90 degrees, because at 90 degrees it stops momentarily for an instant and then comes back. So the idea of the question is clear to all of you. Yeah, Bhargav, what I said is we have to find the value of v0 at the lowest point, that how much speed we should give at the lowest point, so that the particle just about reaches the 90-degree position. It doesn't go beyond 90, but it doesn't stop before 90 also. It just reaches 90, is at rest for a moment, and then comes back, and then goes to 90 on the other side, and like that it will oscillate. Understood, no? So it will behave like a pendulum, but having an angular amplitude of 90 degrees on both sides. Is going to plus 90 on this side, then coming back to the lowest position, then going to 90 on the other side. So it keeps going between clockwise and anti-clockwise 90 degrees without any loss of energy. Yes, very good. The value is correct. Deep, your answer is correct. It's in meters per second, right? What you given? Yes, very good. That's correct. So for those who are completing the first part, just try out the second part now. So first part is find V0 at the lowest point if the particle just about reaches this position. Now second part, if V0 is equal to half the value calculated in part 1, then what is the maximum angular displacement theta for the particle, okay, from the lowest point? Okay, and what is the tension at maximum theta? When it reaches that maximum theta, then how much is the tension in the string? So for this second part, the mass is given as 0.25 kgs this time, or 250 grams. Take G as 10 only. Anybody else got the first part? Yes, Deep, that's correct. Very good. So we'll just take an extra 5-10 minutes today because I started the lecture a little late. Okay, so let's look at the first part. So in the first part, if I'm giving it sufficient velocity that it reaches the 90-degree position from here, that means when it reaches the 90-degree position, it should come to rest. Because it's just about reaching there. No? So this velocity I should give should be enough that the kinetic energy is enough to make it climb through a height equal to the length of the thread. Okay. So if the maximum angular displacement it reaches is 90 degrees, that is at B, then V should be equal to 0 at that point B. So then from A to B, the change in kinetic energy plus change in gravitational potential energy being 0. So minus half mv naught square plus mgh should be 0. But h should be equal to L. So V naught should be equal to root 2 GL, which if you calculate over here, it is 2 into 10 into zero point 0.8. Okay, so that is 4 meters per second. So I have to give it a speed of V naught equal to 4 meters per second. Okay. So from this we understand one more thing, that for V naught equal to root 2 GL, the maximum angular displacement will be 90 degrees. So the string just about becomes horizontal. So this also implies that if my V naught is less than root 2 GL, then the angular displacement's maximum value will be less than 90 degrees. So in that case, it will stop momentarily at some theta max, which is less than 90 degrees. So it will behave more like a traditional pendulum. If I give it a V naught like this, it will reach somewhere here, let's say, and will come to rest. So it will go this way, then it will come back, cross this point again with V naught, then go to the other side, reach that same theta and stop there. Okay. So this is how it will behave in this case. If V naught is less than root 2 GL. Okay, people, so hope this concept is clear. Now let's come to the second part of the question. So this is the second part of the question. If V naught is half the value calculated in the first part, okay, then what is the maximum theta it will reach and what is the tension at that maximum theta point? So this was the first part of the question. Okay, and we saw that for this, the answer is this much. Okay. And the second part, our V naught is half of this value. So this value was root 2 GL, or half of 4 meters per second. Okay. So in this case, what is the maximum angular displacement it reaches, and what is the tension at the maximum angular displacement? This is what we have to see. Okay. So we can see that because V naught is less than root 2 GL, it will behave like this. It won't reach 90 degrees. Okay. So in this case, now what we can see is that we start off the pendulum from here, but with a speed of less than root 2 GL. Then by the time it reaches some acute angle of theta only, it will come to rest. So at some theta max like this, the particle will come to rest because the speed that we are giving at the lowest point, this V naught happens to be less than root 2 GL. So it doesn't reach the 90-degree position. It stops before that. So it will go on either side, but like this. Okay. So A to B. So now use this value. So this height difference is h. You can see that here this is L cos theta. So h is equal to L minus L cos theta. Okay. So A to B, change in kinetic energy plus change in potential energy is 0. So minus half m V naught square plus mgh should be 0. So V naught square should be equal to 2gh. Now substitute this value. So V naught square is how much? V naught is root 2 GL divided by 2. So this is equal to 2 GL into 1 minus cos theta. Because we will substitute this value. H is equal to L into 1 minus cos theta. And we'll substitute this value here. That V naught is equal to half of root 2 GL. So let's see what we are getting on both the sides. So we get 2 GL by 4 is equal to 2 GL into 1 minus cos theta. Or half is equal to 2 into 1 minus cos theta. So 2 cos theta is 2 minus half. So cos theta is 3 by 4. Or theta is cos inverse of 0.75. So that will be the maximum angular difference. You could have also done this numerically. You could have also substituted this way, that 2 meters per second whole square is equal to 2 into 10 into 0.8 into 1 minus cos theta. This would have given us the same thing. So cos inverse of 0.75 . will in fact give about 42 degrees, actually 41.4 degrees approximately. Deep, have you got the same value, cos inverse of 3 by 4? Might have made some calculation mistake, just check. Okay, okay. Because 3 by 5 होता तो 53 होता, but 3 by 4 है ना, so 53 से थोड़ा कम है. Anyway, if you got cos theta equal to 3 by 4, then it's fine. Your calculation up to that point is okay. Just the last step. Okay. Now the next thing is we also want to find the tension at this point. How much this tension is. So the tension at that point B, where theta max is equal to cos inverse of 3 by 4. Okay. So look at the free body diagram of the particle at the point B. Okay. So because the speed of the particle is 0, so the centripetal acceleration should be how much? It should be 0. So that becomes a very important point over here. Tension and mg are acting like this. Okay. So because v is equal to 0 at B, so centripetal acceleration is 0. So therefore T should balance mg cos theta. Okay. And mg sin theta should provide the tangential acceleration. So the particle has 0 speed at this point, but it has a tangential acceleration like this. So that is there because of mg sin theta. So these are the FBD equations. So from the first one, you will get the value of tension. So theta is cos inverse of 3 by 4. So you can see that the tension at this point will therefore become 3 by 4 mg at the point B. And the tangential acceleration will be g sin theta or g sin 41.4 degrees, whatever that value is, that will become the tangential acceleration. Okay, so people, hope this is clear. And with this, we conclude today's session. Next time, we will complete vertical circular motion and we'll discuss the more interesting thing of what happens when V is V naught at the lowest point is greater than root 2 GL because it crosses the 90-degree position. Okay, so it goes into an interesting space. Okay, we'll discuss about that. So try to complete maximum problems from the first part of circular motion that we discussed, banking angle, then friction acting on a body moving in circular path with tangential acceleration and centripetal acceleration and those kind of examples. and make sure you revise the derivations we have done today so far for the vertical circular motion, so you can understand easily the second part of vertical circular motion in the next lecture. Tangential acceleration के लिए g sin theta होगा बेटा, which is sine of 41.4 degrees. You'll have to calculate the value and multiply that with 10. Okay. Or we can also calculate sin theta like this. It is square root of 1 minus cos square theta, no? And cos theta is 3 by 4. So 1 minus 9 by 16. So that will be root 7 by 4. That is your sin theta. So your tangential acceleration will become g sin theta, where you can use this value. Okay. Right. So that's it for today's session, people. Wish you all the best.